Hi. In today's class, we're going to learn about Gauss's law for spherical charge distributions. And Gauss's law for spherical charge distributions has two parts. The first part is if you've got an interior electron. So here's my interior electron. And it's feeling, it has around it an exterior charge distribution shown in blue. The first part of Gauss's law says that the interior electron feels no force from the exterior charge distribution. And there's a second part of Gauss's law. And that one tells us that if we now have an exterior electron, so here's my exterior electron, and we have an interior charge distribution. That interior charge, the exterior electron feels the same force from the interior charge distribution, which is shown here, even if all the interior charge distribution was condensed at the nucleus. So this external electron, shown in red, or shown here in red to the left, they feel exactly the same force from the interior charge distribution if it's in this bigger ring on the left, or if all that interior charge distribution was condensed at the center. Let's give an example to see why this is important. So what I'm going to show here is something from atomic orbitals, and I'm going to draw a ring. And this ring is going to be the band that the 2s electrons make. So these are 2s electrons. Here's a 2s electron, and its location is confined to being inside that ring, as we know from psi squared and from the Bohr spatial diagram. And we're going to put inside that ring, we're going to put a 1s electron. And the 1s electron is confined in a much smaller ring. Here's a 1s electron here in the center. And this is exactly the situation we're talking about. The external electron, the 2s, has interior to it, shown in blue, the 1s electrons. So let's get some space for us to work, and let's now see what's happening. Let's take a look at lithium. So lithium has an electron configuration of 1s2, 2s1. So it has two 1s electrons, and it has one 2s electron, as I've shown in the diagram to the left. And lithium also has 3 protons. So Z is 3 protons. From the point of view of the exterior electron, which is the 2s electron, it will feel the same forces. Here, let me get this. It will feel the same forces as if it will feel an effective force on the nucleus, which will be the 3 protons, but the 2 1s electrons that are here in the center, these 2 1s electrons that are in the center, we can, by the second part of Gauss's law, condense them at the center. So if we condense them at the center, we'll have the 3 protons and condense at the center 2 electrons. So plus 3 for the protons, but now minus 2 for the 2 condensed 1 electrons. And that will then be an approximate Z effective 3 minus 2 of 1. So lithium does not feel a Z of 3. It feels an effective Z of around 1. The actual value, Z effective for lithium, is 1.28. And now we can consider another case. Let's consider beryllium. So we'll do beryllium. And beryllium is 1s2, 2s2. So there are going to be two 2s electrons. I'll call this the 2s electron A, and over here there'll be a 2s electron B. And so its electron configuration for beryllium is 1s2, 2s2. And beryllium has 4 protons. And so now let's see what the effective Z that 2s electron A feels. So we're going to look at it from the viewpoint of 2s electron A, the one that's right here. Okay, it feels, of course, the 4 protons. It feels the 4 protons plus 4. And then there are still those 2 1s electrons that are totally interior to that ring of 2s electrons. And by Gauss's second part of his law, the second part of Gauss's law, that spherical distribution in the interior can be thought of as being entirely concentrated at the nucleus. So it's going to be 4 minus 2. And now we come to the issue of the 2sb. When 2sb is interior to 2sa, well, if it's interior by Gauss's law, it's as if it's concentrated in the center. And if 2s electron B is exterior to 2s electron A, it acts on no forces. So really the question is, what fraction of the time is 2 electron SB, which is somewhere in this ring, closer to the nucleus than 2s electron A, which is also somewhere in the ring? Well, they're both 2s electrons, so they're spending equal amounts of time closer to the nucleus. So half the time, 2s electron B is close to the nucleus, and therefore it can be thought of by the second part of Gauss's law at the center, and that means that it's as if half an electron from 2sb was at the nucleus, and so we can subtract a half. And 4 minus 2 minus 1/2 is 1.5. That's the approximate Z effective. The exact Z effective is known to be 1.91. We'll study and review Gauss's law and Z effective tomorrow.